There are lots of algorithms to perform numerical integration. You can click on this Wikipedia link to see a whole bunch of them. But our focus is on a geometric method based upon rectangles. In the external activities, we consider a stochastic form of integration called Monte Carlo integration. Monte Carlo methods are at the heart of many data science algorithms that rely upon some sort of stochastic implementation and are straightforward to implement in any dimension. Many of the deterministic approaches to estimating integrals are based on partitioning the set A that we are integrating the function over. The idea is, for a partition, is you cut up the set A into a set of non-overlapping collections of subsets, although we do allow for shared boundaries between the subsets. This then allows us to consider the signed areas or volume or generalizations of such concepts between the graph of the function and these subsets as they are drawn on the horizontal axis or plane or hyperplane depending on the dimension for the domain of the function. So some key points here. The simplest such methods for 1D problems involve the use of rectangles or trapezoids, where the areas of such objects are easily computed from rules we've learned in geometry. When A is simply an interval, such as a function defined over the real number line, and we want to integrate it from an interval from A to B, as we've been seeing so far in this lecture notebook, we will typically choose the partition of A to be equally sized subintervals and then approximate the signed area of f of x over each subinterval by simply using a rectangle that is as wide as the subinterval with a height that's given by the evaluation of the function at just some point in the subinterval. When you add up all the signed areas, those being with positive areas being rectangles that are above the x-axis and those with negative areas being below the x-axis, then when we sum up all these signed areas, we end up with an approximation of the integral. Now this is visualized below where we provide some options about where we can evaluate the function f of x. As a suggested activity, add a more useful docstring and doctest to this compute rectangle rules function that's down below. So in this function, you'll notice that I have f, a, b, and n. So f is the function, a and b is defining the left and right endpoints of the interval. This is kind of like what we saw again for the bisection algorithm, where n is now the number of rectangles we want to use, as before n was the number of bisections. And we have a rule that defines if we want to use the left endpoint, the right endpoint, or the midpoint of the interval for evaluating our signed areas of our rectangles and then ultimately getting our approximation of the integral. All we're doing initially in lines 5 and 6 is we're defining the array of points that creates all the little subintervals for our integral approximation. So we have Ix because these are used in the integral approximation. Delta x is determining the length of the base of each rectangle. So you might want to consider this more the width of the rectangle as determined by the length of the base. Maybe it's better to call it width. And then we just control the workflow based on this parameter that is the rule. If it's given as left, then we evaluate the function at all the left endpoints. Notice the array slicing. We are considering all the points, the first point, 0, up to, but not including the last one. So this gives us all of the evaluations at the left endpoints of the interval. If we start at the second and go all the way to the end, we will evaluate the function at the right endpoints of all the intervals. And if we take all the left endpoints and add half of the length of each of these subintervals, we will then evaluate the function at all the midpoints of these intervals. Whichever one you do to use for your values, your y values, that will then determine the heights of the rectangles, whether they be positive or negative, depending on the sign of f. We then sum up all of those values times delta x, and that is summing up the areas of all the rectangles. That creates our integral approximation. So then we return the ix values, the delta x, iy, in this integral approximation as a tuple. So I just run that. That's just a function. Now the function is defined, so now I can experiment with this function, much like we've seen before. What I'm going to do is use lambda functions, either anonymously or just assigning them a variable for ease of reference. And I'm going to use these rectangle rules, this rectangle rules function defined above with the default rule initially. I'm going to analyze the rate of convergence to give you the idea of the concept of how you evaluate the performance of an algorithm. And I'm going to create some interactive visualizations for this that help us tell a story about what the integral is and how well our approximations are working. So here's this function, x plus 1 times x minus 5 times sine of 3x. That's now a lambda function, but it's assigned the variable f. Now for my integral approximation, I'm going to compute the integral, or the approximation of the integral for that function between the endpoints of 2 and 4 for an interval. So from 2 to 4 I want to approximate it. I want to use 10 rectangles. Notice I'm not specifying a rule, so I'm using the default left rule here. And then I'm just going to output the last output, the fourth output, which is the actual integral approximation. Another way to do that, again, is to put like a -1 there instead of that 3. And I'm going to print what that integral approximation is. So it says -1.7. Is that good? Is that bad? Well, we need to study this a little bit more. To study the rate of convergence, like how quickly this approximation converges to the actual integral, we usually vary critical inputs over orders of magnitude and employ log-log plots to understand how errors are reduced by refinements of the inputs. So what I'm going to do is the critical input here is how many rectangles I used. So I'm going to use a log space instead of a lin space. And so this is going to create a set of ins, because I'm going from 1 to 4 with 4 of these. It's going to go 10 to the first, 10 to the second, 10 to the third, and 10 to the fourth. That will be the 4 points. So I'm going from 10 rectangles to 100 to 1,000 to 10,000 rectangles, which is exactly what you will see right here. 10, 100, 1,000, 10,000. You can see clearly that these are a float type. Now the compute rule, the rectangle rules, requires the number of rectangles to be of type int. Why? In fact, actually, in this one, yeah, in this in right here needs to be an int. Whenever I feed this in into it, this linspace is expecting an integer value to say how many points are in there. So if I feed a float number in here, I will get an error. So what I want to do is look at casting that array as a type int, and now I'm going to create an empty list of approximations. And for each in this iterable array of ins, I am going to append to that list my approximation of the integral using that in value for that function, and I'm just going to take the integral value out of it. And then I'm going to show you what those integral approximations look like. So if you look at it, you see, oh, well, even with 10, it was approximately -1.7. With 100 rectangles, it's -1.722 with some other digits. And you see that, all right, they're all pretty close to each other, but they ideally are converging to something. Well, how can I evaluate the error in the quality of these approximations? In this case, I can use the quad function, which was introduced previously, as a way to get a really accurate estimate of what the integral of the function is from 2 to 4. And remember, the first output of that function is the integral approximation, a very accurate integral approximation. I'm going to basically cast my list of integral approximations as an array. That's what that does. So I can subtract the scalar value from every single component in that array. Remember, I can't subtract the value from a list, so I turn that list into an array, and then I can subtract a number from it. This will give me the errors in my left rectangle approximation. So I'll just do that there, and you can actually see something right away in these errors. My error is about 2 times 10 to the -2nd when I use 10 rectangles. When I use 100, it seems to drop by about an order of magnitude. It goes down to about -1 times 10 to the -3rd, and then I get to 10 to the -4th and 10 to the -5th as my next errors. So for every order of magnitude increase in rectangles I use, number of rectangles I use, I seem to drop the error by an order of magnitude. Now notice this error is signed, because sometimes I will over or underestimate the value of the integral, which will lead to positive or negative errors. If I want to do a log-log plot, I'm taking the logarithms of these inputs that I'm giving it. I need to actually take the absolute values to avoid any sign errors, because you don't want to take the logarithm of a negative function. I'm going to plot on the x-axis the number of rectangles used in this log-log plot, and I'm showing as a title that this is the absolute value of the errors versus the number of rectangles using that left-hand rule. So let's just take a look at this. You see a rather linear function. The slope of this function is what's defining the rate of convergence, how quickly it's converging as I'm increasing something by an order of magnitude. So how can I estimate that rate of convergence? Well, you might remember from early on in Module 2 when we looked at some plotting, that polyfit is a way to fit a curve, do some regression to data. So I can take the logarithm data, that I'm working with above, the log of the absolute value of the errors, and I want the slope. So I want the second, I want to fit a line, so that's a first order polynomial, and then the first component that's returned, because it's going to return a slope and an intercept, I just want the slope. I just want this value to estimate the rate of convergence. And I see that the rate of convergence is what it says is -1. The way to interpret a negative value with this rate of convergence is for every increase in an order of magnitude of number of rectangles, I will decrease 1 order of magnitude the amount of error that's in my estimate. That's how quickly this is converging. Let's do some fancier visualization though for this. That's just an introduction to rate of convergence, which is something I have you play with a little bit more. One of the things you might also try to do is play with, I'm sorry, I'm kind of scrolling around here, right here. You could right here change rule to right or to mid to do for the midpoint rule. I didn't, like, that's just the else case, so it doesn't actually check. Basically, if you say something other than left or right, this is what it will do. One of the things you will find with this is what we call first order accurate. It's a first order estimation. It converges with that rate of convergence of -1 is what you're seeing for that slope. This method will also produce that order of convergence. This one will produce an order of convergence that's twice as fast as the other ones. That slope of the line in that log plot will actually be -2. So there's something in the activity to explore for that. But I leave that for you to kind of play with on your own here. I highly recommend just taking a moment, pausing and playing around with that. But these types of code cells are very useful to get comfortable running through and changing some of the inputs as far as the activity goes, what I'm asking you to do. But now we're going to do some fancier visualization. But I think actually this is a good point to maybe pause this part of the video, play with those other estimates, and then continue with this video as we talk about some fancier visualization. All right, it's time to do some fancier visualization so that we can actually see what's going on with all these rectangle rules. So I'm going to define this function, plot rectangle rules. It has that f, a, b, n, and rule parameters, just like the compute rectangle rules. You set some x min and x max values. I've defaulted them to 0 and 1 for visualizing what the approximations look like in a fig number, which is something that we've seen now in some previous results up above. Some previous code, I mean. Now, this first line of code right here is all that I need to actually get the estimate of the rectangle rule approximation for whatever rule I give it. And I'm returning all this other information which is useful for the plotting purposes. I'm also getting the integral approximation, the very accurate integral approximation of the function, in order to estimate errors. All of the computations are basically done at this point. Everything below is just for plotting. So as usual, there's more lines of code involved with doing some visual storytelling. So I'm creating the x and y values for plotting the function. So that's what I'm plotting initially. I plot my typical x-axis, and then I actually create these rectangle objects. This is from the patches collection, the things we were seeing importing before from the matplotlib. So we're going to create these rectangles based on where these x values are and the width and the height. So we create this patch of rectangles, we color them, we add them to the plot, we set the title of the plot, and then we do our typical visualization to kind of clean up how many tick marks and things we have. So that's all that's going on here. I encourage you to again kind of play around and change different values and see what's going on. So that creates the function. I've run this code cell now. I have the plot rectangles function available. Now I'm going to use the interact manual widget for that plot rectangles rule. I'm going to feed it a lambda function, which is, I could feed it the f because it's still defined as the same lambda function, but I'm just showing I can feed a lambda function directly into it. That's fixed. The rule that we're going to feed it is left, right, or middle, and I believe it will do a drop-down box as default if I have this list. Let's see, actually, I think. Yes, if you give it a list with these characters, it defaults as a drop-down widget. I think I did that. I'd kind of forgotten I did that. That sometimes if you don't provide the information, it will try to understand what is the most sensible widget for it. But that's a dangerous thing to do. I should have done a drop-down box, but whatever, it worked. So let's say we have A is 2, B is 4, excuse me, and N is 3. And let's say our rule is left. Let's just run interact. There you go. Here's that curve we've seen a few times now. And you see that we have 3 rectangles, and you see that the height of each rectangle is corresponding to the left value of the function over the subinterval, which you can see by the width of the rectangle where it is. Just like the width of this rectangle is over here, so we see it's negative, it's evaluating the function there, and the left endpoint of this subinterval is right here, and it evaluates that rectangle there. So those three rectangles together sum up to negative 1.35. Sure, it seems like that one rectangle is more negative than the two positive rectangles, if we think about positive and negative rectangular area, than these two combined. And the actual value we know is about negative 1.72. If I increase my n, we see that we have more rectangles, and wow, we get a pretty good approximation pretty quickly. If you were to go back to 3, this is just to help you visualize what's going on with these rectangle methods. So I said 3, so I'll just go back to 3. So there's my left. You can change, if I go right, this value right here should end up, let me zoom in. The value of the function right here should end up being the value associated with this rectangle for the right-hand rule. And the value right here should be associated with the second rectangle because it's a right-hand rule. And then it looks like about right here should be the height of this other rectangle. Let's just go ahead and see if that's the case. There you go. This is the right endpoint now for that first rectangle, excuse me. Right endpoint for the second rectangle. Right endpoint of the subinterval for the third rectangle. And you can see negative 1.24 is the estimate, but again, if I crank it up in terms of the n, it's better. It doesn't seem to be as good as the left in this case, but it's going to converge at the same rate. And then you can see, for instance, let's just bring this back down. It's a little easier to see with less rectangles what's going on when you change the method. If I go to the midpoint rule, the middle rule, you see that the rectangles are being evaluated at the midpoint in the function value. At the midpoint of that interval is determining the height of the rectangle. In that case, that looks like one of the worst approximations we've seen so far. But you go up to, again, like let's say 21, and it's within 2 digits. It's negative 1.7. It's a little off, but it will converge faster. So this just helps to visualize what's going on with these rules and tell the story about the approximations and to convey to a user, this is what these methods mean and how these approximations work. And I have just more functions for you to play with here. Like here's this, oops. So what is going on with this one? No module found, IPyML. So, oh, I have a typo there. That was in a different notebook environment that I'd had. There we go, fix that. I'll leave it in. So if you see anything where I have a matplotlib widget and that gives an error, you have to delete it, that's it. But this is x squared, you're just trying to integrate x squared, and you can see the left-hand rule will persistently underestimate what this value is. It will eventually look like it, if I use enough rectangles, you can see it almost looks like it's getting that area very accurately. But if I use a few, you can see it's a good approximation, but if you zoom in, you see that there's little underestimates because the left-hand rule is evaluating the smallest function value over the whole interval, whereas the right-hand rule, I'll just kind of shrink this in down again, is producing overestimates because the function's increasing on the interval I'm integrating it on. And the midpoint rule, in this case, it does a pretty good job almost right away because it over and underestimates the value. And that's one of the reasons the midpoint rule is generally more accurate, in fact, converges faster. So that's kind of it for the fancy visualizations. Please feel free to copy and paste the contents of this cell into new code cells to experiment with new functions, just so you can play around with the left, right, and midpoint rule with different numbers of rectangles and see what the values look like. But before we kind of conclude, this part goes a little faster than the root finding, is I'm just going to show you how to make a myfunctions rule, because we're using rectangle rules, again, bad dad joke, as a subclass of myfunctionsAmazing, which had some of that quadrature method information on how to plot things with the integrals. So I'm inheriting all the methods from this class, and I'm going to go ahead and initialize that upon initialization. But this one is meant, what I'm trying to do here is just set what rule you want to actually potentially integrate on, as well as how many rectangles you want to use, compute an integral approximation based on that rule. And notice I look at the self.rule is equal to these values, and it's pretty straightforward. I'm just copying and pasting basically the content of other functions into the class methods, and I'm just using the self dot whatever that method or attribute value is. And then I'm going to plot the rectangular approximation, which is just based on that plotting function you saw above. There's really nothing interesting going on here other than I have to have these self.ix, self.deltax, because I'm referencing the data attributes of this object. And then I've created this method evaluate and plot rectangle approx, which just calls all these other methods in order to set up everything for these approximations. And I would say this is pretty fancy, however you want to pronounce this, but I think it's pretty fancy. I'm saying something, I feel like I'm getting bleeped every time I say it, but it's pretty fancy. So this is a fancy function. And I think these functions rule, so you can create your lambda function. Again, you actually don't even need this. You can delete that. That was completely unnecessary. I was just showing things that you can do. You can assign an f, you can write it like this. There's lots of ways you can pass it in. But here's your x plus 1 times x minus 5 times sine of 3x. This is in a really fancy way now. And I can interact with that particular method attribute, the evaluate and plot rectangle approximation. And now everything's just handled within that function. That function has all these other abilities that it's inherited from the class of functions, the structure that I've had in terms of the superclass, the parent class, and this child class. So again, if I run that and I say run interact, there you go. Here's this new function, right? This is this x plus 1 times x minus 5 times sine of 3x. So now I'm trying to integrate it, looks like between 0 and 1. And you can just play with these values to look at how many rectangles you need before you get to like 2 digits of accuracy. Well, even with 376, it sure looks nicely shaded in, but with that left-hand rule, maybe you have to go way up. Oh, it's still off by that 1 digit. What if I go up to 1,000? Oh no, boy, the left-hand rule just is not doing a good job. What about the right-hand rule? That seemed to get it a little bit more accurate. Midpoint rule, I bet I could get it with a lot less. Oh yeah, with 471 there. I can maybe even lower. Oh yeah, 144. That's pretty much spot on. The right-hand rule also seems to be pretty good there. All right. Well, that pretty much concludes this part of the video. I'm just going to end the video with a discussion of the activity instructions and what you need to do there. For the sake of simplicity in this activity, you actually don't need to use any of the classes. Now, I encourage you to. You absolutely can do everything I'm asking you to do using the classes as well. It's just a little more than what's necessary. Here, I would just want you to actually explore more about these different rectangle rules, the left, right, and midpoint, and study some more of that rate of convergence that we talked about. You should feel free to create many new code and markdown cells below as you work through this activity. All those notes I had in the first activity about creating as many code and markdown cells that you want and just exploring, all that stuff applies. So I want you to create a wrapper function that's called multiple underscore rect underscore approximation, approx, which has all the same parameters as compute rect rules, except that the in parameter is now assumed to be an array or a list. Basically an iterable object of integers containing different numbers of rectangles for which the approximate integral should be computed. The wrapper function should loop through all the values in the list of in values, call the compute rectangle rules function to obtain the associated approximate integral, and store all of the approximate integrals in a list that is returned by the wrapper function. Now, is that complicated? That's a lot of words, but honestly, if you scroll up to what I did to study the rate of convergence, I'm basically asking you to put this inside of a function. That's basically what I'm asking you to do. So you just have to add the parameters, and you're basically going to loop through the in and the ins. That's kind of it. So that's going to produce then an array. You're just going to automate that procedure, so you can just call a function to get the list of approximations. So you can store that in a list, and then it should store that list and return it. Now, if you also want, if you want to store that list as an array, if you want to cast it as an array and return it as an array, that's also fine. A list or an array. An array might even be better for the next part. What I want you to do then is for a number of different lambda functions, including the following. Basically, f of x equals x, f of x equals x squared, and f of x equals x cubed. In at least one of your choosing. Try a trig function. Try something different. I want you to compute the errors for the left, right, and midpoint rules for every single one of those. Within the array of in values, and maybe you want to call it ins, but I just called it in here, to be 10, 100, and 1,000. You could also use log space and use more, but you do at least 10, 100, and 1,000, and let a and b be 0 and 1 respectively. I want you to store the errors as either a list or a numpy array, and to compute the errors, you need to either know the exact value or a very accurate approximation of the integral of the function, what I suggest you do is use quad. This is basically asking you to do this part where I want you to compute arrays of errors, just like what I was doing here up above. And I want you to do this, I want you to assign these different variable names for each of your different functions and for each of the different approximation types. And then for every single one of those that you did, I want you to create a log-log plot, just kind of like what I've shown above, with a legend that shows the errors for each rectangle rule approximation versus the number of rectangles. So if you're plotting it with the left rule, have something that says this is for the left rule or the right rule or the midpoint rule. And then I want you to plot that versus the number of rectangles. And so I'm saying create a log-log plot for each of your functions that has these 3 plots on it, the left, right, and midpoint rule for each function. So each function gets its own plot, That plot will have 3 curves plotted on it. The label for each curve should contain the information related to which method, left, right, or midpoint rule, was used to approximate the integral. You will then use a legend to display what the different curves are. And you'll do this in a log-log plot. That's what I'm asking you to do. And I want you to then analyze the rate of convergence to see how the errors decrease as we increase the computational effort, meaning the number of rectangles that we use. And I want you to estimate the rate of convergence for every single one of those functions with each method using the np.polyfit function. So, and again, make sure to use that np.apps. You should basically be following the code I had above as like a template. I then want you to comment on and interpret your results in the markdown cell below. Some questions you should try to answer are the following. Which method appears to be the most accurate, converge faster? Spoiler alert, it's the midpoint rule. But there are some functions where you might find that, it's hard to estimate the rate of convergence. Why is that? Because effectively it's exactly accurate right away. Why is that? I want you to think about why that is. In a sense, I can tell you the midpoint rule is effectively helping to balance the cancellation of errors of over and underestimating a function in general as the subintervals get small enough. What do I mean by that? I think those pictures, playing with those images and those functions and graphing things will help you get the picture in your mind about how to explain this kind of conceptually correctly. Creating the visualizations of the approximations of the integrals with a small number of rectangles does provide the insight. This is what I'm suggesting you do. So that's it. I'm not going to do this for you because it's kind of just following the code I had before, but just making sure that you are assigning new variable names and putting it all together correctly. I really want to see you do that. Hopefully these instructions and pointing you to what code you can effectively copy and paste and just edit different variable names and make your own approximation functions really helps you out. If you have any questions, post to the discussion board on Canvas. I'll be happy to answer there or come to office hours. After that, I just want you to go through your activity for the summary for integration, and that's it. Thanks for listening. I know this is a long lecture notebook. There's a lot of material in here, a lot of things to play with, but there's a lot of great takeaways that you can have in here and a lot of kind of themes that will play out in terms of your career in working with code and data in computational science that hopefully you find very useful for years to come. The external activities will be due the week after this one. Although if you're listening to this video, that will depend on who's teaching the class and if it's in a 16-week, effectively using finals week as another week, versus an 8-week format like in the summer or some other format. But for our class, I will have this one notebook take 1 week. I'll give you 1 week to do this whole thing, and the external activities will be due the week after it. So that's it. Thanks for listening again. Good luck.